Everybody, welcome to Math 470. This is the part 4 on the lectures on field extensions. This is actually the third video as we did the first part in class. Once again, I am recording this in my workshop, and I just want to warn everybody, for some reason, the Air Force is enjoying flying well right above my workshop at nice low altitude. So I've had to scrap this video at least once because of jet noise. So if you hear a jet buzzing in the background, I apologize, but what do you know? The Air Force doesn't listen to me. Okay, so let's get down to it. Where we've been so far, we've seen the Kronecker extension theorem, where given a polynomial, you can find a field that contains a zero of that polynomial. We have then looked at taking sort of minimal field extensions, taking a field, adding an element on, and looking at the smallest possible field that contains both. We've seen in one case, it's the field of fractions of basically the polynomial ring when it's transcendental, and otherwise when it's algebraic, it's a nice vector space that's spanned by powers of the element, up to one less than the degree. Last time we saw finite field extensions where you have two fields where one is a finite dimensional vector space over the other. And today we're going to see another large classification, namely algebraic extensions. We have been looking at a single algebraic element, and in the finite field extensions, we started to look at adding maybe a couple of algebraic elements. Now we're going to look at extensions that are very algebraic. It's going to turn out that we will see that every finite field extension is algebraic, but the reverse is not true. There are algebraic extensions which are not finite dimensional, and we will see that towards the end of this video. Okay, so an algebraic extension is pretty much exactly what you would expect it to be. We call an extension to be algebraic if whenever I take something in the extension, it's algebraic over the lower field. Okay, so this means that given any element in E, it is going to satisfy some polynomial with coefficients in F, or in other words, E doesn't have any transcendental elements with respect to F. Now, most of the extensions we've seen so far are indeed algebraic, and they are usually the ones that we like the most. All right, so case in point, let's look at, say, Q adjoined I. And we claim this is algebraic. So if I take any element in here, it has to satisfy some sort of polynomial. Well, if I take something from Q, there's nothing to show. It's just going to be a zero of x minus itself. So anything is algebraic, any field is algebraic over itself. All right, on the other hand, if I do take an element with a non-zero complex part, all right, then I can take x minus a plus bi, and then I can take its conjugate as well. When I multiply that out, I get a quadratic, but 2a and a squared plus b squared, they're both rational numbers. So this polynomial is in the polynomial ring over Q. Because of its factors, it has a plus bi as a zero. So there we go. Alpha is a zero of this polynomial, hence it's algebraic over Q. All right. Now, as mentioned at the beginning, we've already seen a large class of these, namely finite dimensional extensions. Every finite dimensional extension is algebraic over the base field. Okay, so to prove this, what we have to show is if I start with some element in the extension, I can find a polynomial with coefficients in f such that f of u is equal to 0. Now, if we were to try to do that constructively in the abstract, it would be horrible. It just doesn't work. We don't have enough information to just pull out a polynomial. That having been said, it's not too bad. What we do is we use linear algebra. Okay, we know that it's finite dimensional. That's got to be key to the whole thing. So what I do, I take E over F, and I assume it has dimension n. Now, since its dimension is n, we use a fact from linear algebra that's really, really powerful and important here. If I have an n-dimensional space and I take any collection of vectors, I don't care what they are, but there's more than n of them, that collection of vectors is necessarily linearly dependent. All right, now, how does that help us here? What we're going to do, we take our element, u, and we start taking powers. And I'm going to take enough powers. I'm going to start with u to the 0, u squared up to u to the n. Well, that now gives me n plus 1 vectors inside an n-dimensional vector space. So this collection has to be linearly independent. There is just simply no choice. Okay, well, that means that I can look at the homogeneous equation. So I can set up an equation C0 times 1, C1 times u, up through C n u to the n equals 0, and I can look for solutions for it. Now, the vectors are linearly dependent, so there has to be a non-trivial one. Namely, I can guarantee a solution where at least one of these coefficients is non-zero. And in fact, since we're working in a field, if u is non-zero, none of these powers are 0, hence at least 2 actually of these coefficients must be non-zero in this case. All right, but that gives me a relation involving u, involving powers of u, that get me 0. All right, so from that, I just extract the polynomial with those coefficients. I know at least one of the c sub i's is not 0, so this is not the 0 polynomial. But if I evaluate it at u, well, I just get this equation back, and I get 0. Hence, u has to be algebraic over f. I have found my polynomial using linear dependence. Now, 2 things to note. Number 1, we haven't actually found the solution. That could be pretty messy depending on the value of u. All right, the other thing is, while we have found a polynomial, this method doesn't actually guarantee that you're going to find the minimal polynomial. Now, that having been said, if you find such a polynomial, you just would have to factor it. Again, it would depend on the field how nasty that factorization would be, but one of the factors would be the minimal polynomial. Okay, so that gets us for us. We started with an element u, we have found a polynomial for which it is a 0, hence it has to be algebraic. So every finite extension is automatically algebraic. Now, that in and of itself gives us some very strong results. Okay, in particular, if you take 2 elements, alpha and beta, that are algebraic, then algebraic is a nice property. If I take an inverse of one of those, it'll be algebraic. Their sum, their difference, their product, again, all algebraic. Now, if you were to go at this using the definition, okay, so you might be tempted, well, so if I know the minimal polynomial for alpha and I know the minimal polynomial for beta, maybe I can figure out the minimal polynomial for alpha plus beta or alpha minus beta, etc. Yeah, don't. Just don't. It doesn't work. Okay, so to give you an idea, let's compare the following numbers. All right, so root 3, root 5, and then there's some square root 3 plus root 5. Now, root 3 and root 5 are both algebraic. All right, this is easy enough to tell. X squared minus 3 has root 3 as a 0. X squared minus 5 has root 5 as a 0. I need a polynomial which has root 3 plus root 5 as a 0. Okay, we've constructed a minimal polynomial once before in class, and you're going to have homework doing this. There's no hard and fast rules for it, but the trick that we're going to use here is similar to the one that we did in class as well. I think that one was only quadratic. This one's going to turn out to be quartic. But this is the general approach, and we hope that it works. So what we're going to do, all right, I am going to call alpha square root 3 plus square root 5. All right, now I need a polynomial relationship involving alpha that gets me 0. So I need to take powers of alpha. If I start taking powers like this, though, it could get a bit messy. So what I'm going to do, I'm going to isolate one of the radicals. It really doesn't matter which one. Okay, I'm going to square that out, which gets me this. All right, now this is an improvement. This equation had 2 radicals in it. This equation only has 1. Keep in mind, I'm wanting something with rational coefficients, so I have to somehow eliminate all radicals. All right, well, that's not too bad. I'm going to isolate this radical and then square it out again. When I do that and then bring this over to the other side, I've now eliminated all of my radicals, and I have that 0 is equal to alpha to the 4th minus 16 alpha squared plus 4. All right, so that gets me a polynomial x to the 4th minus 16x squared plus 4. Now, is this the minimal polynomial? It's not actually important that it is, but it is. And since I can show you that, I think I will. Okay, so to check that it's irreducible, I just have to sort of go through the options. So if it's irreducible, or sorry, if it were to have a 0, then it's easy to check that, well, it doesn't. Okay, a 0 would have to be a divisor of 4, so plus or minus 1, plus or minus 2, plus or minus 4. You can check, none of them work. So if it doesn't have zeros, it can't factor as a linear times a cubic. So the only way it could possibly factor if it did would be into 2 quadratics, so 2 2-degree polynomials. I could set up those 2 possible equations. I could crank out the factors and see if I can solve it. Get this, it won't solve. Or on the other hand, if you notice, this thing is quadratic in x squared. Okay, so if I were to substitute y in, this would be y squared minus 16y squared, sorry, y squared minus 16y plus 4. So that being the case, I could use the quadratic formula to find the values of x squared that would make it 0. Now, this gives us a quadratic factorization, admittedly involving real numbers, not rational numbers. Okay, but that's enough, because if it had a factorization over q, then these would have to be associates of that factorization. So I'd have to be able to multiply through by an invertible real number and somehow wipe out all the radicals and get rational numbers when all is said and done. But that can't happen. In order to wipe out this radical, I would pick up a radical on the x squared or something like that. There's just no way to do it. So because this factorization exists and is quadratic but isn't rational, it has to be irreducible. All right, now, if we look at these 3 minimal polynomials, there's no relationship between them. It's not like I can take this one, multiply it by that one, and get this one, or some simple transform that involves these 2 to somehow get this one. There's just nothing there. Okay. Now, root 3, root 5, those are pretty straightforward algebraic numbers. There's nothing fancy there. And if it's not working here, it's not going to work in general. Okay, so starting with the minimal polynomials of certain elements and trying to manufacture the minimal polynomials of numbers they generate i.e. sums, products, inverses, it just doesn't work. We have to use something else. Okay, so how are we going to show things are algebraic then? All right, we use a really, I think, cool idea. What we do is, rather than trying to construct these polynomials, we know that every finite extension is algebraic. So in order to show that an element is algebraic, we simply find a finite extension that contains it. Okay, because if it's in a finite extension, everything in there has to be algebraic. So that'll solve our problem. Okay, so if you go back to the corollary, one of the first things we want to show is that alpha inverse is algebraic. Okay, well, if alpha is algebraic, then f adjoined alpha has finite degree, namely the degree of the minimal polynomial of alpha. All right, now, it's a finite extension. It's also a field. So if alpha is in there, which it has to have an inverse. So alpha inverse, whatever it is in f adjoined alpha. That's a finite extension. Hence, alpha inverse is algebraic. All right. Now, for alpha plus or minus beta, okay, well, last time we saw that when you successively take fields, their degrees multiply. Okay, now, if I take the field with alpha and beta adjoined, well, that's at most the degree of alpha times the degree of beta. It could be smaller. Beta or alpha could factor over the other. We don't know. But it doesn't matter because this is still finite. Whatever its degree is at most this, but that's finite. And this, because it's a field and closed, has to contain alpha plus beta and alpha minus beta. Hence, they're algebraic. All right, and if you think about it, the same thing works for alpha times beta, because alpha and beta are both in here, hence their product is in here. So those are all algebraic, and we get them to be nice and algebraic without having to construct any polynomials. Okay, so with that established, we can define something called the algebraic closure. Okay, so I have a field extension f contained in E. The algebraic closure of f is simply all of those elements alpha in the extension that are algebraic over f. Note, this is dependent upon what E is. If I take different extensions, I will get different algebraic closures. So what this does is it takes f and it adjoins anything to f that is algebraic. Now, what we showed in the previous corollary, so we showed that the sum and the difference of algebraic elements is algebraic, the product of algebraic elements is algebraic, and we've shown the inverse of an algebraic element is algebraic. In other words, if we take an algebraic closure, we get yet another field. This field is, in some sense, the largest algebraic field we can find that contains f that is a subfield of E. Now, what's more important to us is the notion of what's called an algebraically closed field. So a field is algebraically closed if whenever I have a non-constant polynomial, it automatically has a 0 in the field. So I don't have to go out and extend it in some way to do it, to find it. Okay, now there is the canonical example of an algebraically closed field that you know is the complex numbers. Okay, if you take a complex polynomial, it will have a 0 in C. This is part of the reason we like the complex numbers. Now, proving that fact, on the other hand, is not easy. In fact, There is no straightforward algebraic proof of this fact. You can do it using purely algebraic means, but it's messy. It takes a lot of machinery to put together in order to get the result out. Okay, so there's that. The other thing is, one of the things that makes it very difficult to prove it algebraically, C contains the real numbers. The real numbers are an analytic object. If you remember from Math 360, the real numbers have the least upper bound property. That is a property strictly about R. Q doesn't have it, and almost all algebraic structures don't have it because it's something that allows for limits. We don't have limits in algebra. Well, we do, but I'll get to that later. But because it's got that distinctly analytic object in there, it's almost impossible to use algebraic methods to show that it is indeed algebraically closed. So this is one of those things, again, should we resume in-person lectures, I might show you some of how it works. It's not hard to sketch out. In fact, that was part of the problem I assigned you. I said to prove that any odd degree polynomial in R has a 0 in R. That right there is actually the obstruction. The way you prove that is using the intermediate value theorem. Requires continuity. And that's the thing that makes it proving that C is algebraically closed difficult using only algebraic methods. All right, so on the other hand, something is algebraically closed if and only if every non-constant polynomial factors into degree 1 factors. So this is sometimes referred to as splitting. It takes a polynomial and you can break it down and everything is nice in degree 1. Okay, so to see this is reasonably straightforward. If it's algebraically closed, then the only irreducible polynomials have degree 1. If I were to have one that didn't have degree 1, then I could find a 0 of it. But if I have a 0 of it, then x minus alpha is a factor of it. But it was supposed to be irreducible, so it can't have factors, then that's a contradiction. All right. So all of my irreducible polynomials have degree 1, but then every polynomial is factorable into irreducibles. Okay, so everything can be factored into irreducibles. All of my irreducibles have factor degree 1, hence everything can be factored into degree 1 polynomials. All right, the reverse is also true. So if everything is factorable into degree 1, well, I take a non-constant polynomial, it has to have a factor, some ax plus b, so I factor that out. So, but when I do that, negative b over a is a 0 of this, so I can just plug that in and I get 0. Okay, so it has a 0 in the field, that makes it algebraically closed. So those two things go hand in hand. A corollary of that is that if you have something that is algebraically closed, it has no proper algebraic extensions. You can't find something larger than it that is algebraic. All right, proof of that is, again, reasonably straightforward. If I take something in E, well, that is algebraic over F, it has a minimal polynomial. Well, minimal polynomials are irreducible. F is algebraically closed, so its irreducible polynomial has to be x minus alpha. So this has to be a polynomial with F coefficients. Well, that does it. If this has F coefficients and alpha is one of those coefficients, alpha is in F. And that's it. It must be it. All right, now this one, again, if we go back to in-person lectures, I may show this one. There's a very important fact that if you have a field, you can find an algebraic closure that contains it. Okay, we talked about algebraic closures earlier in the sense of belonging to some large field. This is not the same. This is, I start with a field all on its own, and I take algebraic elements from everywhere and I throw them on, and I eventually can close out the field. This is a non-trivial fact and requires the use of something called Zorn's lemma, which is very powerful in set theory. It's, again, I think every math major should see a proof that uses Zorn's lemma. And again, if we return to classes in person, I will show you this one because it's an important one. But Zorn's lemma is a little weird the first time you see it. And so I would rather do that in person. Okay, now, where do we go from here? That covers the basics of field extensions. What I am going to do next, I am recording this before classes have officially resumed, so I'm still working on my plans. But one of the things I'm going to do is I'm going to have all of you submit questions about these videos, about some of the readings I'm going to give you, and I'm also going to go through the textbook and choose some problems and so forth. And in the next video, I'm going to show you some methods that we use to solve and prove results about field extensions. All right, well, until then, well, wash your hands, everybody. You're supposed to do that.